Hello and welcome. In this video, we're going to take a look at a new kind of integral called a surface integral. And just like with line integrals, there are a couple different kinds of functions that we might want to integrate. We could integrate either a scalar function or a vector valued function. And in this video, we're going to be taking a look specifically just at integrating that scalar function over a surface. So let's start off with some of the basics here. Remember that if we've got a parametric surface in terms of u and v, then we could think about that parameter domain here as being this region D. And to keep things simple for the moment, let's just imagine it's a rectangle. Going back a little ways, if we were going to be just taking a look at double integrals of a function of two variables, then all we did was we just divided that region up into little sub-rectangles, delta x and delta y, and I'm doing the same thing here. I'm just dividing that big rectangle up into sub-rectangles with delta u and delta v. Now, when we map that with our parametric equation, r of u and v, we end up with a surface in our three-dimensional space. Now, if we are going to be integrating some function of u and v, then we can think about just picking a single point in each of these little sub-rectangles, let's say ui star, vj star, and we'll plug that into our function, and that gets us a point in three dimensions here, p star, with some kind of x, y, and z coordinates. Let's say xij star, yij star, and zij star. And those three coordinates, of course, just come from plugging in ui star and vj star into our parametrization. Now, we want to evaluate this function of three variables at every one of those points. And that will give us a value of f in each of these little sub-rectangles, which, of course, now that they're curved, we could think of those as being little patches. So we're evaluating f at a point on each patch now. And then we will simply take that value and multiply by the area of each patch and add them all together. Now, the area of each of these patches, we can kind of go back and take a look at how we calculated surface area, and that will be a very similar process. But let's just call the area of that patch delta s ij for the time being. Then what we are trying to do here is sum up over all of the patches from I equals 1 to m and j equals 1 to n, plugging the point into the function, multiplying by the area of each patch, and then if we take the limit as m and n go to infinity, then we get the definition of our surface integral of f over the surface S. And you'll notice that this is very similar to the definition of the line integral, with the difference that here we have little patches on the surface instead of little sub-arcs. We have delta capital Sij instead of little delta s, little sub-arcs. Now, of course, this is just the definition, and we don't really want to calculate it this way, so we just need to go back to how we calculated surface area of each of these little patches, delta Sij. And if we remember, we actually calculate each of the area of those patches by approximating using the tangent plane and the vectors given by the partial derivatives of r with respect to u and v. Now, if you remember from a previous video, each of the areas of these little subpatches is approximately equal to the magnitude of the partial derivatives ru and rv cross product together, delta u, delta v. But as m and n go to infinity, we say that ds is equal to the magnitude of the cross product ru and rv dA. And that will allow us to turn this surface integral into a double integral. And so as a result, if we wish to integrate f over the surface S, then we will turn this into a double integral over the parameter domain D in terms of u's and v's. So we'll have to plug in our parameterization. X will be a function of u and v. Y will be a function of u and v. Z will be a function of u and v. So that's going to take our scalar function in terms of x, y, and z and turn it into a scalar function in terms of u and v. And then to turn this from a surface integral into a double integral, we just have to remember that ds can be replaced with the cross product magnitude dA. And there we are. We are able to now calculate the surface integral of a scalar function. Now, if we have the case where our surface isn't parameterized in terms of u and v, but maybe our surface is simply a function z equals g of xy, then this can be simplified a little bit. If we have the case where we have a surface of the form z equals g of xy, remember that we can make a parameterization out of that. we can just have a parameterization r of xy equal to x, comma y, comma g of xy. And using that little clever parameterization, we can derive a convenient formula for the surface integral of this function z equals g of xy. In either case, we will be switching from a surface integral to a double integral. And d is either the parameter domain, or in the case of a surface z equals g of xy, then d is just the projection of our surface onto the xy plane. All right, well, let's try an example or two. Let's start off with an example of a surface that can be written in the form z equals g of xy. Here, we want to evaluate the surface integral of the function xz ds, where s is a triangle with vertices on the x, y, and z axes at these 3 points. And it might just help to try to sketch that triangle first. And there is our surface, our triangle going through those 3 vertices. Now you see how z is in our integrand, so we really should get a function z equals g of xy so that we can make our integrand in terms of just x's and y's. So let's see if we can come up with the equation of this surface. Now there are several different methods that you could use to come up with the equation of this plane, but because it is a very basic plane and it's easy to see our partial derivative of z with respect to x and z with respect to y, what I might suggest here is let's see if we can just get that normal vector really quickly. We see that the partial derivative with respect to x is straightforward since we are dropping z by 6 every time we go over 1 unit in x. So that partial derivative g with respect to x must be negative 6. Now we can also see that our partial derivative of z with respect to y is negative 3, since you can see we are dropping 6 units for every time we go over 2 in the y direction. So our partial derivative of g with respect to y must be negative 3. And we've seen in the past that we can just get a normal vector to a plane by a simple formula of negative g partial x, comma negative g partial y, comma 1. In this case, that would be 6, 3, 1. And from there, we can find the equation of the plane by taking that normal vector dot product with x minus x naught, y minus y naught, and z minus z naught. And here I'm just using the point 1, 0, 0. That gives us the equation z equals 6 minus 6x minus 3y. But you may have been able to get right to this equation even just by knowing that it must be a linear equation in x and y. It must have an x-intercept of 6. And you can see those partial derivatives right there, negative 6 and negative 3. You might have been able to jump right to that. With that function, z equals g of xy, we can now write xz as x times this 6 minus 6x minus 3y. We also have the partial derivatives of g with respect to x and g with respect to y, so we can replace ds with the square root of gx squared plus gy squared plus 1, dA. And now we're ready to find out what this domain D is going to be. And that is simply projecting this triangle onto the xy plane. So now we need to look at this green triangle here that I'm just shading in on the bottom. We can use the vertices to be able to find out the equations of the boundaries of that triangle. Now, because this region on the xy plane is a fairly simple region, such as a triangle here, we could use dx dy or dy dx, depending on whether we want vertical or horizontal rectangles. I'm going to suggest we use dy dx. That means that we need the equation of the top boundary here to be of the form y equals a function of x. We just need the equation of a line passing between the 2 points 0, 2 and 1, 0. That's simply y equal to 2 minus 2x. And so the boundaries of our region here will be from x between 0 and 1, and any rectangle that we draw between x equals 0 and x equals 1 will have a bottom boundary of 0 and a top boundary of 2 minus 2x. So let's turn this double integral into an iterated integral now. All right, now that we've got this as an iterated integral, dy dx, we can integrate with respect to y from 0 to 2 minus 2x, and then we can integrate with respect to x from 0 to 1. We'll start with integrating with respect to y, and then plugging in y equals 0 and y equals 2 minus 2x. And from there, well, we'll have to expand out a whole lot of terms here and start collecting them. And don't worry, it all turns into a nice polynomial here. And then we can integrate with respect to x. And from there, we can plug in our boundaries x equals 0 and x equals 1. and we get the square root of 46 over 2. All right, now that we've seen how a surface integral works for a function z equals g of xy, let's see if we can try this with a parametric surface where x, y, and z are given in terms of parameters such as u and v. For this example, let's start off with S being a helicoid, parameterized by v cosine u, v sine u, and u. So you can imagine that that is kind of like having a corkscrew in a way. And we're going to use u from 0 to 4 pi, so that should be 2 full rotations, and v from 0 to 1. Now, we're going to try evaluating the surface integral of this function rho of x, y, z equal to the square root of x squared plus y squared. And if you kind of want to get a sense of maybe an application for this, we could maybe think about that as being sort of like the density of this very thin corkscrew. And its density is 0 when we're at the z-axis, but the density will increase as we get further away from the z-axis and x and y both increase. Now, by adding up the density on each of the small little patches on our corkscrew, we get the mass of this corkscrew. So that's essentially what we're calculating right here. Let's see if we can first start off by turning this surface integral into a double integral. We're starting off with the surface integral of the square root of x squared plus y squared over this helicoid. And remember that ds is just equal to the magnitude of ru cross rv dA. So we will need to find the two partial derivatives of our helicoid, and those are fairly simple to calculate. Ru is equal to negative v sine u, v cosine u, and 1, and rv is equal to cosine u sine u comma 0. Now we'll have to find the cross product of those two vectors. And remember, this is the normal vector to our surface. And once we find the cross product, we can see that this third component, negative v sine squared u minus v cosine squared u, well, we can pull a negative v out as a common factor, and we're left with sine squared u plus cosine squared u, which is equal to 1. That simplifies our normal vector very nicely. Now, for each of these little elements ds, remember that we need to calculate the magnitude of that cross product. Calculating the magnitude of that cross product, we're seeing another sine squared u plus cosine squared u, which is equal to 1. So this all simplifies down to just the square root of v squared plus 1. Now we're ready to turn this surface integral into a double integral. And we'll also have to plug in our parameterizations of x and y equal to v cosine u and v sine u respectively. Plugging all of that in, we now have a double integral over the parameter domain D, which is given in the question. So we're just about ready to turn this into an iterated integral, but we should simplify this up nicely. You can see here we've got another v squared cosine squared u and v squared sine squared u, a common factor, and another identity of cosine squared plus sine squared. So in the end, that gives us our integrand, v times the square root of v squared plus 1, which is already setting itself up very nicely for using a basic substitution. Now, let's turn that into an iterated integral. Let's integrate with v first from 0 to 1, and u second from 0 to 4 pi. We can do a substitution for v squared plus 1 and use the power rule. And then I'm going to substitute back again and have my antiderivative in terms of v. So the antiderivative there after substitution rule is v squared plus 1 to the 3 halves all over 3. You can check that by taking the derivative. Now we need to evaluate that from v equals 0 to v equals 1. And we can pull that 1/3 out of the integral. When we evaluate from v equals 0 to v equals 1, we get a constant, 2 to the 3 halves minus 1. So since we're just integrating a constant from u equals 0 to u equals 4 pi, that's simply just going to multiply that by 4 pi. And we are left with 4 over 3 times 2 root 2 minus 1 pi. And that would be essentially the mass of this corkscrew given that density function. And there we are. That's basically just turning surface integrals into double integrals. We're pretty comfortable with double integrals at this point, hopefully. And so you can just translate all of those skills onto a three-dimensional surface. The key is just knowing how to take that ds in the surface integral and change that to dA using one of those two conversions, depending on whether we have z equals g of xy, or if we have x, y, and z all given in terms of two parameters u and v. Now, in our next video, we're going to be taking a look at a different kind of surface integral where we're going to be integrating a vector function, and that can be interpreted a little differently. In this last example, you might have thought, well, okay, that's kind of like the mass of a corkscrew, but it's going to be completely different when we start integrating a vector function, so stay tuned. Thanks for watching, and I'll see you in the next video.